Now, your half-life is just the time it takes for half of the sample to decay. Okay. And I think you guys eventually will do a lab with like M&Ms. I think you can use Skittles too. For a half sample. Sometimes my pen writes really well, sometimes not so much. I'm thinking it's probably user error. Okay, and like I said, the shorter half-life, the more dangerous it is. That's the term they use on your test, dangerous. And like I said, they don't show half-life on here, but let's say you have like 100-gram sample of something. After one half-life, you'd have 50 grams. After two half-lives, you'd have 25. There's actually a like an actual formula with like fractions, and it's really complicated, and I never figured it out in order to do half-life, but I've just always done it this way. Another half-life would be 12.5, and then you could go on and on. And let's say each half-life was like 7 years, right? So then each one of these arrows would represent 7 years. So if they asked you, how long did it take to get to 12.5 grams, or how long did it take to get to a quarter of your sample, or I guess it's not a quarter of your sample, but 12.5% of your sample. Well, let's say they did 12.5 grams. How long did it take to get 12.5 grams? You just do 7 times 3 because you went for 3 half-lives, and that'd be like 21 years. If they said, how long did it take to get to a quarter of your sample, that's only 2 half-lives. So then you could do 7 plus 7, or 7 times 2, you'd get the same answer. 14 years. And so that's how I've always done half-life problems. It seems a lot easier to me than the fractions and stuff. So if you need this for your labs or whatever, try this method. It seems a little easier. I honestly haven't watched the nuclear physics instructional videos for this unit, so I don't know if they do the easy way or the hard way in your if we talk about nuclear physics, we have to talk about fission and fusion. So both of these will convert matter to energy. Okay, fission is what happens on Earth. And fusion is usually on the sun. We have been able to make some fusion reactions on Earth. They've done some experimentally, but at this point, fusion on the Earth takes up more energy than it actually produces, because fusion has to be really, really hot. Like I think I read like 100,000 Kelvin. And so in order for it to get that hot, in order to get the fusion reaction to occur on Earth, the scientists have to put in more energy than they get out of it. So it's not a useful form of generating energy at this point on the Earth. And the way I remember fusion versus fission, fusion has a U and sun has a U. And so that's how I remember that they go together, and then the other one is Earth. It's silly, but that's how I remember it. In fission, you're going to separate things. Okay, so you're going to separate 2 atoms, or separate 1 atom usually. And produce energy. And I'm just going to use a big E for energy. In fusion, you're gonna fuse things together. Okay, so they're gonna come together and produce energy. Traditionally, like on the sun, fusion actually does produce more energy than fission. It's just that we can't get, like, naturally occurring fusion will produce more energy than naturally occurring fission. It's just that we can't get fusion to happen on Earth very well. In fusion, it needs to be very hot. I know I said that before. Um, and then a cool thing about fusion is because you're not separating things and you're bringing things together, there's no waste. So, like, if you guys have taken environmental science or AP environmental science, you discuss nuclear energy a lot. And one of the problems with the nuclear energy we have right now is it's fission. And so you have all this waste product, and a lot of it is very highly radioactive. And so then there's the problem of trying to store that waste where you want to put it. Um, nobody wants nuclear waste stored by their house. You don't want to have it somewhere where you could get a hurricane or a tornado or an earthquake. It has to be very stable geologically. Some people say put it in the bottom of the ocean. Is that a good idea? If it leaks, we don't really know. And then we've got like radioactive ocean. So there's this big whole issue with where do you put the waste? Well, if they can get fission to or fusion to work, then you're not going to have that waste issue. And then they have this term that they want you to know, and it's called critical mass. And basically, what the critical mass is the that mass at which you're going to get an uncontrolled chain reaction. In a nuclear power plant, they want a chain reaction, but they want it to be controlled. They want to try and control it a little bit because they want this starting up the fission process uses a lot of energy. So if they can get the fission process where it's just a chain reaction where it keeps occurring and occurring and occurring and occurring and occurring, then they don't have to worry about starting it up all the time. And they try and control that. They have these control rods and they raise them and lower them out of like the core. It's like a water area in order to control that chain reaction. Well, if you hit critical mass, then you're going to have an uncontrolled chain reaction. And then you can't stop it. And that's what they try and avoid. And I'm going to write Rx in for reaction because I don't know if I have enough space to write the whole word reaction. And so this would be a formula with fission. You can see we've got one element here, uranium, and it's separating into these two elements. I want to say that's krypton and maybe barium. I don't know. I don't know. Like I said, I don't have these memorized. It's been a while since I taught chemistry. Now, one of the things your test asked, which was I thought kind of like a weird question, is they said, what does this 3 stand for right here? And you see you've got this like 1 neutron there, and then you have 3 here. So what this is saying is this is saying that for each reactant, for each uranium atom, you're going to have this happen 3 times. Okay? And so that's kind of what's going on. That's what that is telling you. And so this is your neutron. You've got 3 neutrons, and then this E stands for energy. And this is the part that we want. Okay, so this is a fission reaction. You can see you've got one thing and you're breaking it into 2. So that's how you can tell it's a fission reaction. You just kind of have to just look for the elements and kind of tune out the other stuff. And then if we want to look at a fusion, you can see we've got 2 things and we're turning them into 1 and we're releasing energy. Okay, so this would be The other one was like a decomposition reaction. This would be like a, I don't remember what the chemistry word is actually for a where you're putting two things together. But you can see that you've got two reactants and then the one product. So that would be a fusion reaction.